That's not about. I close the door. Okay, so we're doing square root of, oh, surprise. 18 squared plus 24 squared. So what am I looking for?
It's equal to 900.
It's equal to 900?
Yep.
Or the square root of 900?
Well, 18 squared plus 24 squared.
Okay, cool. So,
But then you have to take the square root of.
yeah, but that's such a huge number. Can we even think about taking square root of such a big number?
I would say so. Yeah.
So the square root of 900 is 30. Okay, so we could do it like that, kind of brute force. We know that we could do some arithmetic and come up with a 900 here and come up with a 30. Okay, so that's one way to look at it. What's another way? What's that, Nathan? Just know the date. Yesterday was the 29th, so today's the 30th. So that's obviously equal to 30. Did anyone else do it that way? It's not a bad way to do it, but I do want you to check the math from time to time. Kieran.
You can divide 18 and 24 by 6.
Okay.
And then you get 3.5, and then you can multiply it by 6.
So what concept are you talking about here?
It's 9 is right triangles.
Right triangles. Oh, so you recognize that this is a version of the Pythagorean theorem, it sounds like. So 18 and 24, since we could divide both of those by 6, we could simplify that to be, oh, that's the worst right triangle ever. Okay, that's not much better, but okay, 3, 4, and 5. So going this way, we divide, you said, by 6.
Yeah.
Going the other way, we have to multiply by 6. So I hope that makes sense. That we get a 30 there. It sounds like you did both ways. Nice. Any questions? I'm gonna pose one other way, just kind of to have a little bit of algebra fun, because who wants to know what 18 squared is? 24 squared? Maybe you already know. I don't know, but I do know that 6 squared goes into both of those. So I'm going to just factor out 6 squared, leaving me with 3 squared plus 4 squared. Does that make sense? You could do that? Okay. Square root of 6 squared, of course, is 6. Now we just have this, which maybe is more easily recognizable as 3, 4, 5. Or at least 6 plus 9 plus 16 is a little bit easier to do, but yeah, ultimately I'm looking for you to see a triangle when you see expressions like that. So that's the pre-warm-up. You ready for the actual warm-up? I can't hear you. You guys ready for the actual warm-up?
Yeah.
Yeah. Pumping it up. Here we go. 2 questions. One's a throwback. One's a throw in. Throw in. Not a throw out. Definitely throw up. I hope not. You never know. No. No. I didn't. I've had people verbally throw up. It comes out, you can't control it. Check with your neighbor about your graph, make sure that they did it right. Make sure you did it right. Where's all of You're no longer a peninsula.
Migrating.
Migrating. Okay.
What two periods? Two periods.
I wanted, here's my graph. Let's say,
Horizontal by one half. And vertically by the same. And it's moving in the top. Yeah. That's nice. Oh, ready?
That would be normal.
Because then pi is divided by 3, pi by 2, and then pi is 3 divided by 2. You multiply everything on one. Oh, so why is it so hard there? So 2 pi times 1/2, 2 pi times 1/2 is. Actually, it's not. It's the one. It's 2x becomes h times 1. It's sine of 2.
Am I ready? So go over it.
It's been kind of.
Give me 10 more seconds. There's still a little discussion going on.
Yeah. Yeah.
Oh.
Oh, you just like no.
5, 4, 3, 2, 1. Okay, please show me. Did you all bring your pocket sign graphs? Please show me your pocket sign graph. Normally it goes from 0 to 2 pi. In this case, can you tell me what happened to your normal sign graph? You got it. Squash. Looking at the period is now from 0 to pi. Okay, so hopefully you can grab something like that. Why am I still writing in red? It makes no sense. So 0 to pi. So how many points do I need to graph sign? 5 points. Going up to -1, up to 1, down to -1. So something like this. Is that right? Does it go on? It does go on. How far? As far as you want. You want to go 8 periods? You got them. You want to go 100 periods? We got it. You could do that. If you want to waste your life making 1,000 periods, you can. Let's not do that though. Okay. Are we good though? Let us move on to this next one. Obviously not related to the last one. Sine of 2x equals 1/2. Who'd like to help us with this? Kieran.
I did sign inverse.
Okay. So you got 2x equals sine inverse of 1/2 like this.
Yeah, and then I solved sign inverse 1/2.
Okay. Is this true? Sine inverse of 1/2 is 5/6.
And then I divided by 2.
Okay, either divide by 2 or multiply by
1/2.
1/2. So x equals pi over 12. Is that right?
Yeah.
Any questions? Okay. Well, this is correct. Yeah. Are there more, right? It's important not only be correct, but also be complete. I believe this is true. If we plug this 5 and 12 in, Here, 2 times 5, well, it is. However, it's big, but another time 5, which is 1/2. So what would the other solutions? I really don't know. I didn't. Oh, okay. How many did you get? You got 4. There are, okay, don't say more, but yes, there are 4. I'd like for you to do the test where the other one. Where the other one? That's all you want to do.
Yeah, that's right. That's why like it was. Oh, you really get there. Yeah. I thought those 4 answers. Okay.
Okay, let's go over this. So, Andrea, I'm gonna let you take the lead since you mentioned that there are more solutions. How did you think about this? Should I start over or?
Just add another period, right?
Okay, so we could add, and why would we do that? Okay, so what you're saying is you could visualize the answer to question number 2 in this graph. Can you see that we could do that? It's asking for a time that you have people to 1/2. Hopefully you're visualizing this line. And you can see that there are clearly between 0 and 2 pi, there are 4 solutions. But how do we get them? So Andrew, I'd like to know how you did this. Are you comfortable speaking about it or?
Well, my previous approach was somewhat valid, but
Okay.
I feel like I got the first 2 valid.
Okay. Okay. So pi over 12 and 5 pi over 12. Let's see if that makes sense according to our graph. So you're saying that right here is pi over 12. Do we agree that that would be accurate on the graph?
Okay.
And this right here, if we're counting in 12ths, this is 6 pi over 12, isn't it? If we're counting in 12ths, it's 6 pi over 12. So you're saying 5 pi over 12 is another one? I like it. No, that sounds like you have something to share with them, or a question maybe. Ah. That's fantastic. That was really nicely said. What do you think? Does that make sense? Should I go over that one more time?
Yeah.
Yeah, that's really nice.
Oh, you
Like
should.
on another.
Yeah.
It makes sense.
It is.
So I'm going to talk about this kind of how Andrew started and how Nola continued. I'm going to first continue with Andrew, the way Andrew was doing it. And I do want to offer you a warning about inverse trigonometry. Be careful about inverse trig. It only gives us
one answer, when it might be more. So use it when necessary, but if you don't need it, just don't use it, meaning. Find out something with 1/2, don't know that that's something that equal either 5 or 6, or 5, 5 or 6. But we get more solutions. Like, find something with 1/2, that's something, I think that something has to be 5 or 6.
And I think this goes with what Nola was saying, right? That plus 2 pi over k. Yeah, so I am gonna get to that in just a second. So I'm gonna skip this and just go right to this one first, 5 pi over 6. And then just multiply both sides by 1/2, so we get 5 pi over 12. But we do see that there aren't quite.
But there might be some more. So to get this one quite quickly, we would build off of this pi over 12 and just add. To make some pi on it, now we. Over 5, we go just add pi to get to that number. Pi over 12 with pi is. 35 over 12, and to get this other one, you would start there. 5 pi over 12, you get add pi, that's to get your.
13 pi over 12. And your 17 pi over 12, is that what it is?
Yeah.
17 pi over 12. So that's how to do this kind of analytically or conceptually. Like, you know, the idea that a sine wave is doubled in frequency, there's going to be more solutions in our same interval from 0 to 2 pi. I'm gonna see if I can go back to it. Yeah, there we go. Okay, another way to do this, and this is kind of more what Nola was talking about, is to say here that 2x has to be equal to either 5 or 6 plus the general form will be 2 pi k, or 2x is equal to 5 pi over 6 plus 2 pi k.
Okay, so same idea. Kind of what equals 1/2. Well, that one is either equal to this or equal to, it just happens to be 2x. Now, from both of these, you like multiply all sides by 1/2.
Which gives us x equals pi over 12 plus pi k, or x equals 5 pi over 6 plus pi k. And from there, 5 pi over 12. Thank you. Thanks for listening actively. So now what we could do is say, well, let's find values of k for which we have answers that lie in our range. In other words, I'm going to say that k equals 0. When k equals 0, x equals pi over 12 and 5 pi over 12. And now I'm going to see what happens when k equals 1. When k equals 1, we're left with
Pi over 12 plus pi. With 13 pi over 12? Yeah.
x equals 13 pi over 12 and 17 pi over 12. 17 pi over 12, is that still in our 0 to 2 pi range? Yeah, we could also say that k is equal to 2, because remember, k is just an element of the integer, so I'm just counting up 0, 1, 2. Let's see what happens here if I'm doing a.
Yeah, I think for the 2 is pi over 12 plus 2 pi. Obviously, outside that range, 0 to 2 pi. 2 pi plus 1, so I'm out of that.
All of our 4 answers. These 4. Any questions? So be careful when solving the trigonometric equations. It's important to not only be correct, but to also be complete. The fact that they started with sine of 2x had the effect of doubling the number of solutions. My normal 0 to 2 pi. If it was sine of 3x, if I would triple that, instead of 4 solutions, it would be 6 solutions. Tripling the 2. I'm gonna ask you to now consider the question sine of 1/2 x equals 1/2.
Think about it, and it's easy, don't answer that thing. You've got to be neighbors, and,
When you have a plan. Could you show me how many solutions it has? And do you have an idea how many solutions it has? Yeah, it's still from 0 to 2 pi. Yeah, it's from 0 to 2 pi. No one know? I see a couple people closing answers. Okay, there's definitely more than one, so make sure you complete it. Okay. So how many answers does this have? How do we know it has two? 0 to 2 pi and, okay. Okay, so when you're adding that 4 pi k, you're looking ahead algebraically. And if it's adding 4 pi k, it doesn't make sense to add any 4 pi k. Okay, so we just have the original twos. Any other way to know that we have two solutions? Yeah, Noah? Adriana?
And then if you put it in shape of when you're I don't know that you're gonna have to that on the
Doesn't matter.
For us,
I know what you mean exactly. We care about it.
care about it's not-
We embrace it. Yeah, we're gonna ignore it for a little bit. Does that make sense? And if you visualize the graph, it's like, what were you thinking this by any chance? Like, no. Yeah, okay. Right, if we have this, again, we're just wondering where this hits that line, y equals 1/2. There's gonna be two places. Okay, and to get them, who can help me through?
Oh, yeah.
What's that? Yeah, to get the x values. Yeah, Andrew, you wanna take it? What do we do this? Oh, interesting. Yeah, so just kind of relabel it here. So whereas this used to be pi over 3. Is that what you're saying? I'm not sure what you're talking about, relabeling. Yeah, cool. Well, don't want to do it graphically, and graphically will tell us there are two solutions, but it's a little dangerous unless you have a very accurate graph about getting the solutions there. I just want to know what are the two solutions and how do we get there. So not graphically, but algebraically or conceptually speaking. Oh, not in the graph. I just mean not back to the problem. Yeah, Karen. Okay.
And then you know what sign and y and really one not and y has to be either 5 and 6, 5 and 6.
Okay, so this is either equal to 5 or 6, 5 or 6, or 5 or 6.
And then
Okay. When you said the y thing, are you doing a substitution? Is that right? Just kind of simplify things. Okay, you could do that. One for y. Yeah, I'm just going to go ahead and put the whole 1/2 x. Just multiply everything by 2. Pi over 6 divided by times 2 is pi over 3, and the other one times 2 is 5 pi over 3. That's all we're looking for. That's all we're going to get from 0 to 2 pi. Any questions? I heard the homework took a long time. It was pretty action packed. An hour and a half. Well, yeah, and everyone takes different. Like some people take like less than an hour, some people take more than 5 hours. Hopefully, the homework should never take you longer than 2 hours. My aim is between an hour and an hour and a half. So if it's outside that range, like in the long direction, please let me know and see if I could help you out. So maybe we'll get back to some of that, but perhaps what we just did today could help on some of the problems that may have given you a hard time. Because it wasn't always just sign of x. I think some of them like sign of 3/2 x or something like that. Okay, but let's go on to the new topic, and maybe if we even gets to new stuff today. But let's talk about this problem. This is on page 18. It's not the day before break, it's the day before the day before. So is it Wednesday? It's either Tuesday or Wednesday. I forget what day it is. I think it's Wednesday. No, we only had one thing. So we get to cosine of x equals -1/3. You're already there, aren't you? And you might be a little bit annoyed by this. Why would you be annoyed by this question? Yeah, Noah. Yeah. Can we take a moment just to appreciate the unit circle? It's so nice when the numbers they give us work out like the -1/2 or √3/2. It's so nice, isn't it, to just be able to know the angles that it refers to like that. So hopefully that you're there. So it should lead to some frustration when it's not a number like that, but we could still use the unit circle. You could either use unit circle or you could use triangles. I'm gonna do a unit circle. I'm just kind of a pretty big unit circle guy. Okay, the fact that it says cosine of x equals -1/3 means I'm looking for angles whose x coordinates give us the -1/3. Does that make sense? So I'm gonna mark this -1/3 on the x-axis. I'm gonna look for the angles that have this as an x coordinate. You see where they both are? Quadrants 2 and 3. So I'm going to mark that like right here and right here. So what I'd like you to do right now is to find those angles in degrees. round it to the nearest tenth, which means you're gonna have to use the calculator. You have to use a calculator because that negative 1/3 is not part of the standard rotation. So you do it. Oh, so we are ready to go. Remember to keep the calculator in which mode for that? I asked for degrees for this one, just because it's gonna be a little bit more intuitive. Oh. Make sure the neighbor knows how to find this angle. In fact, if you want to use your phone, it's your weapon. That ability is not on Snapchat.
I'm trying to find my line to the calculator. Yeah, that's it. Oh, yeah. Thank you.
Oh, but then you guys. What do you ask? You ask him to start off saying.
Oh, what question? Go back.
Yeah. My friend said information about the data.
Oh, wait, first time, always standard, yeah, always standard. Okay, we've had a pretty long time. I'd like to, I put an arc there. I'd like to know what's the angle there. Andrew, did you get it? What did you get?
This is 109, 109.5.
Good. Oh, wait, for the first one, can we verify that, 109.5 degrees?
Yeah.
And I don't want to hear the next one just yet. So I'm gonna say that X is approximately 109.5 degrees. Is that a surprise that it's 109.5? Visually speaking, we knew it was gonna be in the 90 degrees, it's no surprise. But in readings, it might not be. Is it a surprise that when you did the work in the calculator, it stood out this anyway, like opposed to 105 degrees? Why is that not a surprise? Exactly, cosine inverse will only be the that's its range, that's all we're doing. It's up to us to get the other angle. Did you get the other angle? Yeah. That's probably the angle we're supposed to do. 360 minus. Does that make sense to do a 360 minus? All the way to 360 and then coming back to. Oh, just go directly this way. You get negative 109.5.
I mean, 271.
Oh, and that, I think that got you the same thing, right? Negative 109.5. I don't want to talk about what we just did. The other answer was 250, is that right? 105. Now, Nathan, would you mind sharing us with us what you did that up? That's really interesting.
I don't know if like my view is I added and I keep those five. Okay, so you found the measure of this and right here? Yeah. And then I did the third thing. Does that make sense?
Yeah, no,
I like it. Very good. I originally not to do it, not to cut the angle into pieces. And it works, just be careful. Yeah, this is good.
Of course, it's not really the answer to our question, is it? Why is it not the answer to our question? And use a negative division. It can be degrees or radians, it doesn't specify. It's important to not only be correct, but also to be complete. We have two solutions that are between, I don't know, negative 180 and positive 180, but we want all of them. So let's separate this. So x is approximately 109.5 degrees. And the other one is x is approximately negative 109.5 degrees. What are we going to add to them? Are you good with that? Adding 2 pi k? No. 360k. We're in degree mode here. Well, you'd be skipping answers if you say plus 720k. So I hope that this makes sense. Are we good with that? Notice I put the little squiggly equal sign, that's also called approximately equal to. So if I wanted exact answers, then I would have to say x is equal to, is it possible to make it exact? If we do radian? Radians, we need a nice place like on the unit circle, like if it equals negative 1/2. Negative 1/3. And we have an idea. Yeah, that's the best we can do. Well, let's do this in radians. Cosine inverse of negative 1/3 plus 2 pi k. And x equals, the other angle would be either 2 pi minus cosine inverse of negative 1/3 or negative cosine inverse of negative 1/3 plus 2 pi k. If you're in radians, it'd be fine to say 360k plus 360k as long as you're indicating that we're in the. Any questions? And so again, please note the difference between approximately 15 is when you put actual equal signs here. I might take out the point. Not more than one for the whole test, like you repeat a little bit, that might take out one point for this way. Because you remember, it's not equal, it's approximately equal. Anytime you're rounding, it's approximately equal. Like, if you put approximately, you can do that, and that's exactly the point. Why be mindful about what you're doing? Got it? Okay. So that's the first of two topics there. That's actually finishing up the topic we did last time. Andrew? Yeah. In order to do that, I recommend looking at the graph. As we switch gears and to give you all the time to think about Andrew's question, I'm going to give you a few minutes to just kind of let this percolate. If you need to stretch, that's a good time to do that. We'll start again at 2:29.
I just got a snack for that. Actually, don't.
Okay, let's get started. Well, let's continue, shall we? Should be excited. I should credit for that. It's too late, but I appreciate that. Next one, you have to be the first to say it. Yeah. Okay, so after finishing up equations like we just did, I want to get to identities. Do you remember what identities are in equations? What does it mean if an equation is an identity? It's always true, no matter what you plug in. Does anyone remember any identity that we've studied? A squared plus b squared equals c squared. Is that an identity? That's definitely a theorem.
No. Sine squared plus.
Ah, sine squared plus cosine squared equals 1. What kind of identity is that called? What do we call Pythagorean identities? We had a name, like an abbreviation. Ident. No. Eoid. No. It's right here. Did we say PID? Pythagorean identity? Did we call them that? Did I neglect to call them that with you guys? Okay, my bad. How many Pythagorean identities are there? There's 3. So PIDs. I'm gonna write down the first one. Sine squared theta plus cosine squared theta equals 1. RID. What does RID stand for? Any idea? Reciprocal identities. What is the first reciprocal identity we learned? Nathan, do you remember? Oh, nice. Like you just pull it from your brain right there. Okay, so that's one of the, how many reciprocal identities are there? Really, just 3? I think there's 6 of them. Okay, so aside from those, there was also quotient identities, oops, QID. But let's talk about the first one. I think it was tangent of theta is equal to sine theta over cosine theta. The cos is fine. And the last one I want to remind you of today is EOIDs. Standing for even odd. I'm going to start you off on the first one. And I'm going to be quiet now as you list as many as you possibly can without referring to your notes if you can. If you need to, then you may. Two of these, three of these, six of these, and six of these. So you're listing all of the identities you can remember.
I put how many are. There's things going on. You say the goal is that also when
Nicely said, yeah.
back up.
Yeah, that's another one. Good. And you said sine theta is equal to, I cut you off, sine theta is equal to what? Thank you, nice. Want to check in on your neighbor, make sure that their list is going okay and it's correct. Yeah, finish up the even odd identities. If you haven't copied these yet, I'll give you a chance maybe a little bit later, but you do have to know all of them. I have things to be memorized or at least understood. We know the sine of negative theta is equal to what? Negative sine theta, which means the sine is what kind of a function? An odd function, which means that the graph is symmetric over the origin. Are we good with that? Could you picture that? The sine wave being symmetric with respect to the origin? Cosine of negative theta is equal to cosine theta, which means cosine is what kind of function? An even function, which means it's symmetric with respect to the y-axis. Could you picture that with the cosine? Both of them doing this kind of thing. Same thing on either side of the y-axis. Sine of negative theta is tangent negative theta is negative tangent theta. So, and then of course, the reciprocals mirror the original, so negative cosecant theta, secant theta, and negative cotangent theta. Yeah?
Yeah.
So you have to know these identities. But there are many identities that you're gonna see that you don't have to know. Because these identities, things like these, are the problem. And what it's gonna say, prove the identity, or establish the identity, or consider, not consider. There are other ways. Yeah, but prove and establish, they're often do it. Now, when you actually look at this, is we start with some number second equation, but you have to prove that it's equal. Because of that, you cannot do the normal equation kind of stuff. You can't add stuff to both sides because that's the assumption that they're equal. You can't multiply both sides by the same thing. It's the assumption that the two sides are equal. What you have to do is keep them independently. Both sides independently, simplify until they match. Does that make sense? We're not gonna move stuff around. We're gonna simplify independently until the two sides match. So let's do this problem. Normally you take the side that's messier and work on that one. So we're gonna start with the left side. What can I do with cotangent theta over cosecant theta? In fact, that cosine over here, you're probably gonna want to change all of these, like break it out of cotangent and cosecant, break it down from there, just sine and cosine. So it's the cotangent, although you're right, it's one of the tangent. I'm gonna say that cotangent theta is what is that, cosine theta over sine theta over 1 over sine theta. Yes. So we are doing a proof here, and you've done proofs in another class, haven't you? Remember what we have to do when we do proofs? Statements, reasons. We just give a statement. What's the reason for that statement? Quotient identity is one of the reasons. And reciprocal identity. So I want you to tell me what you did. Like mathematically speaking, what did you use there? It's actually a substitution using these two things. Okay, should we have a given? We could. The problem is kind of a given thing. You don't have to write that though. We'll just jump right into the first step. Next step, there are different ways you can go with this, but I'm going to say that this is cosine theta over sine theta. You know what I'm about to write? Times sine theta over 1. What's the reason for that? Yeah, maybe definition of division. Now this is very informal. If you just want to put division, I'm fine with that. If you just want to put the sign, that is fine. You do not have to write it as an if-then statement. You miss those days, if-then statements, but yeah. No. What's that? Oh, you don't. Oh, Hudson. Extra credit. Okay, so have a division there, and you see what happens next. Oh, I should be putting equal signs here. We cancel, leaving us with cosine of theta equals cosine theta. Now I've been pretty lazy here because it's always the same thing. I'm simplifying the left side, I'm using the right side, going to equals cosine theta. In the end, I do want to see cosine theta equals cosine theta to fly in the box. I do want to include the equal sign. Remind ourselves that we're a balancing equation here. So, and what's the reason for cosine theta equals cosine theta? The reason is like, how did we go from here to here? Simplify, cancel. I'm gonna say cancel. Yeah, that's fine. If you want to say simplify, that's fine. If you want to say division, because it's division, sign divided by sign is 1, which is now gone. Cancel. Let me see if I can write that like a human might. Cancel. Okay. Close. Any questions? Okay. Oh, after a proof. It's very traditional for a mathematician to write 3 letters. You know what these 3 letters are? That isn't therefore. That's not a proof. You have an idea? Sabrina, you have an idea? QED. Have you heard of this before? QED? Qued. It's not actually a word. We never take QED, which is an acronym for a Latin phrase. I think I heard it before.
What?
I don't speak or take Latin, but it stands for quod erat demonstrandum. I believe it's what it is. Is it? I should say. Do you take Latin? Oh, so it just means it has been shown. It has been shown. QED. So it's optional. You don't have to put it down, but it's just kind of nice after a proof. I did it. I showed that it's true. In English, it means it has been demonstrated. And a joke amongst mathematicians, because we only tell bad jokes, is that it stands for quite easily done. Yeah, it's really bad. I'm sorry. Did I tell you the joke about the 0? I forgot if I told this class. Did I tell you the joke about the 0? What did the 0 say to the 8? No, that's another math joke. Nice belt. Yeah. Oh. If a 0 wore a belt. Yeah. Okay, moving on.
Oh.
It's so bad. It's so bad.
Yeah.
Yeah. It will always work at a party, though. I hear. I've never been invited to a party, but I hear it always works at a party. So, yeah. Like a math party? My dream. But every day is kind of a party, right? Every day is kind of a party. Celebrating life, math. Thank you. Extra credit. Celebrating extra credit. Okay, so I told you that we simplify the more complicated side, and then I gave you a problem that is equally complicated on both sides. So this one is kind of unfair. I feel like you immediately a trick problem, and what we're going to do is work on the right side and leave the left side alone. Even though we could have worked on the left side because it, again, equally complicated. So I'm just going to leave that left side blank. The right side, what I'm going to do is I'm going to rewrite it. I'm going to multiply top and bottom by a special quantity, 1 plus sine of theta. Of course, if I do that on the top, I have to do it on the bottom. It's like when we have that square roots, exactly. Okay, so the reason for this, what reason am I going to put like, I don't want to hear about any identity. Identity property of multiplication, which means you can multiply by 1. So I'm just going to say times 1 is okay. You multiply by 1. Now I want you to multiply out the top, but leave the bottom factored and just watch the magic unfold. So multiply the top, distribute the top, but not distribute the bottom. Enjoy the show. Please don't call anything out, but everyone discover the enjoyment for themselves. Again, you're multiplying out the top, you're distributing on top, but do not distribute the bottom, leave it factored. Second neighbor. The magic. If we think it right, there should be a, oh. You have to see it though. You have to see, oh, I heard an oh. I heard a thing. There we go. You're just playing with my emotions now. So mean. Oh. Yeah, okay, so on the top we have 1 minus sine squared theta, the bottom we have cosine theta. Now, at this point, there is no O moment. Right now it's, what's the reason for what I've just done? This line, multiplication, so multiplication. Okay, but the next line. What's gonna be? Where'd that cosine squared theta come from? Do you see it in our list up here? Do you see 1 minus sine squared theta? Do you see it? That's the O.
Oh, 1 minus.
That's the O. 1 minus.
Oh, it's like a function thing. Oh.
There is an O in it. There's also the C, S, and theta. Yeah. Yeah, sorry. Yeah, actually credit, thank you. We're gonna try to mapify that. So what's the reason here? PID, yeah. And then it's so pretty, isn't it? Yeah, we cancel one of those cosines, so the cosine theta on top. 1 plus sine theta on the bottom, and what do we do next? Oh wait, what's the reason for this? Cancel. What do we do next? You leave it because it matches the left side. All right, we're done. So this is an identity, that the first problem is an identity. We just proved that it works for any theta, but please don't memorize it. And now, what 3 letters? Q, E, D. Yay.
Anyone ever memorize every identity?
But then you can't prove it, and so that wouldn't work. And you could memorize all of them. Thousands. Thousands. If you're memorizing them like I did, you're probably not going to be invited to many parties. So. Okay. Now this one, which side are we gonna work with?
The left side.
The left side. I'm gonna tell you the conjugates don't play a role in this one. And one hint is that what there was on the right, that is handy. You're mindful in reading substitution here. And what we are. I'll give you a chance more time.
Wait, you have been there when this is.
You is just a variable, it's an angle. David's a variable. The angle could represent an angle.
Ooh, somebody might want to- Say, look at the see which comes in the- Yeah, what is it? Oh, yeah, what do you multiply that? One minus.
Get that one across. Oh, so you have to go find that one. You can't multiply both sides, so only do one side. No, but I think if you do one, they're all. Not equal to each other. Leave the bottom on the side.
And then.
Is anyone getting it?
Let's see. Oh, no. Oh, you actually did it. Wait, Tony. Let me do that. Yes, you actually did it. Wait, that's actually like one.
And then you multiply top and bottom by 2, so that's the.
I didn't really. I didn't have that.
Would you ever get into problems where it doesn't work?
Oh, like prove an identity and it's not an identity, not on purpose. That'd be so mean.
Yeah.
I'm mean, but not like that mean.
All right.
Yeah, that all the time.
Like prove these triangles are congruent. They're not congruent. Like that. Oh, really? Okay, so I'm gonna go over this, there are usually several paths to the correct answer, so neither one is more correct than others. Sometimes the path that you choose will lead to a brick wall that's 1,000 feet tall, which means you have to start again and try something else or fix your error. So what's that? Or you can try climbing it if you like. But there's probably a shorter path around this wall. So I'm gonna work with the left side. I'm gonna leave the top 1 plus tangent of u. On the bottom, I'm gonna write 1 plus 1 over tangent of u. Now remember, the other side just has tangent of u, so I'm gonna try to keep it in tangent land. Now the reason for what I just did is RID. Next, I really hate little denominators in a fraction. So what I'm gonna do is I multiply top and bottom by tangents. That on top it becomes tangent of u times 1 plus tangent of u. And on the bottom, when I multiply by tangent, I'm going to actually distribute this through, so we get tangent of u plus 1. So the reason for this is times 1. I multiplied by 1. You see what happens next? A plus b and b over a are equivalent. That's why I could just cancel these, leaving us with tangent of u equals tangent of u. For what reason? It's canceled.
I hope it makes sense, 1 plus 10 here, and these are one and the same thing. They can't.
No, there are other ways to do it. I think that's the most efficient way for this one. But the other ways are not wrong. As long as you are logically solid. Oh, I can't forget to write. QED, yay. What does that stand for? No, the real one.
Quo and for me.
Quod for numius. Quod erit demonstrandum. Probably demonstrandum. I speak no Latin, obviously. I have one more question for you. The one time. Here's a question. I was gonna give you a warm-up, but I think it was too complicated. I think you can do this now. What's
Is it a plus?
Oh, no, this is not an identity. This is an equation. Step one. Make it so it's all the same trig ratio. We don't want cosines and sines together. So I'll give you a chance to work on that. Just one trig ratio. Not sines and cosines. So this is not a warm-up, but a cool down.
+3.
Yeah, cosine of x plus 3 equals 2 times sine squared of x. We know that sine squared of x is equal to
Oh, sine squared x is cosine.
sine squared of x is equal to, let me check my identities up here. Oh, no, they're not there. So sine squared of x is equal to, you see it? 1 minus cosine squared x, just to get everything the same trig ratio. That's an important first step. Once you get here, the next step is factor it. I think there's anything you could factor out. There's no common factor other than 1. You can factor it. If you want to make a substitution, you can. I'm going to urge you to try to break away from that. 2 cosine x and cosine x. Like 1 and 1. I think there's not a lot of options here. We're still on the interval from 0 to 2 pi. Just let's do from 0 to 2 pi. You see what those solutions are? I think we've done problems similar to this today. So 2 pi over 3, 4 pi over 3, and pi. No? That makes sense? And so x equals, oops. X equals 2 pi over 3, 4 pi over 3, and pi. Oh my goodness. I wish I could keep you longer, but you probably have buses to get to and homes to get home to. I'm gonna put the identities up here one more time, just in case you want to copy it down. Have a wonderful day, folks. We're going to take a picture of my lovely handwriting. Oh, just a moment. Let me.